say that chemistry's my hustle, and your brain is like a muscle. So settle in because it's time to flex. Hello, chemistry students. Mr. Didier here. I hope you guys are all enjoying the nice weather. I'm going to go over the last learning target for gas chemistry in this video. Before we get there though, I've got a little review on the top of the note sheet. Hopefully you've had a chance to print this out. We've got combined and ideal gas laws, and what I'd like to do is review how they are similar and different. You can pause the video now if you want to copy these down. I'm just going to start going through them. Obviously, we have two different equations. One is P1V1 over T1 equals P2V2 over T2. The other one being PIV-NERT, or PV equals nRT. So clearly different equations. Also, let's talk about the variables that are involved. Both gas laws have pressure, volume, and temperature. The big difference between combined and ideal gas law is that ideal gas law includes moles of gas, and you're going to see that gas constant there. Speaking of gas constant, the other thing that they have that's different about the two is that combined gas law does not have a gas constant in it, but ideal gas law does. And that gas constant, the one that we use, depends on the pressure units. For instance, if we have atmospheres for our pressure units, then the gas constant that we use is 0.0821 liter atmosphere times Kelvin mole. And if you're wondering, how do I know which one to use? We did copy down which our gas constant goes with which pressure unit in our 12.2 notes. Lastly, and this is kind of a big one here, this last row here says when to use. Basically, the big difference here is that with combined gas laws, whenever there's a change in your pressure, volume, or temperature. So you're going to be given multiple temperatures, pressures, or volumes within the problem. It'll say something like, if the initial pressure is this, or if the initial temperature is this, and then it changes to this, so that's a change in temperature there, and you're usually asked how either the volume or pressure will respond to that change. With the ideal gas law, though, it's whenever you're given an amount of gas, or asked to solve for amount of gas. So moles or mass is the big thing that you should be looking for. If you see moles or mass, then you know to use the ideal gas law. You'll either be given the grams/moles, or you'll be asked to find the grams/moles. Any mention of amount, and then you are going to be going towards ideal gas law. I also put here, it's for gas stoichiometry. And you may not know what I'm talking about there for good reason. That's what this video really is about, is gas stoichiometry, which is our last learning target, 12.3. The subtarget says, I can determine the volume or amount of gas that either reacts or is produced in a reaction using gas stoichiometry. So think about this essential question. How can gas volume measurements be used to calculate out relative amounts of reactants and products in a reaction? How can we take what we learned in stoichiometry back in Unit 8 and include gases? Well, we're going to go back to the mole road. Remember, let's copy down the mole road again. Hopefully you recall some of this. We have grams of some substance, we'll call it Z, can be converted to moles of Z. And that would be using a molar mass. I'll just write molar mass right here. Notice the double-sided arrow, we can convert back and forth between them. But we could also have moles of some other substance, call it Y, which we can convert to grams of Y, and that would also be using a molar mass. Of course, it'll be a different molar mass because it's a different substance. At the heart of stoichiometry, what we learned in Unit 8 is that you can convert from one substance to another. That requires a mole ratio. That's stoichiometry. But now think of this, this question here. Can you think of a way that we could include volume in our mole road or our stoichi road here? Where could we include volume? I have included a hint for you. Remember that we have this equation that says PV equals nRT. Now that you've had a chance to think about this, where could we include volume? Well, if we have moles of the substance, we can convert that to volume because we have an equation that relates moles to volume. So we could actually put here, let me choose a different color. Let's go orange. We can convert to liters of Z. Maybe I'll just put, let me change that from liters. That's the actual unit, but I'll just put volume of Z. We can convert from moles of Z to the volume of Z because we have an equation, and the equation is PV equals nRT. And we can do that with a different substance as well, like Y. We could convert moles of Y to a volume of Y. And again, that would be using the equation PV equals nRT. So all we've done is we've added another step onto our mole road that we had before. We can convert from moles to volume. Or think about it the other way. We can now convert volume to moles. What we need is an equation. It's PIV-NERT. And that kind of assumes then we're going to have some information about pressure and temperature if we're going to convert from volume to moles. So watch out for those when we try these next three examples. Example 1. Water can be produced from hydrogen and oxygen in a synthesis reaction. We've got a balanced reaction here. I'm just going to balance this out quick. You can pause the video and do this yourself if you'd like. I'm going to keep going here. We have 2 oxygens on the reactant side, so now we have 2 oxygens on the product side. We have 2 times 2 is 4 hydrogens on the product side. That's 2 times 2 hydrogens on the reactant side. Now we're balanced. How many grams of water, so that's what we're trying to convert to, can be produced from 5 liters of oxygen and excess hydrogen? Remember the rule that we learned in stoichiometry. If you see excess hydrogen, don't worry about it. We've got a lot of it. It's like you open the refrigerator and you've got a whole bunch of cheese and a couple slices of bread. The determining factor on how many sandwiches we can make is going to be the 5 liters of oxygen, or the bread in my example. Okay, and we're also given temperature and pressure. There it is, STP. Remember that at STP, temperature equals 273 Kelvin, and pressure equals 1 atmosphere. Okay, where do we go from this? First, think about what we're given. 5 liters of oxygen. Where would that be in our mole stoichi road? Well, it's volume, and let's just call it our first volume. Volume of Z, that's what we're given. And we're asked to find how many grams of water. Where would that be on here? Well, it's grams, so it's either going to be the far left hand or the far right hand side, and it's a different substance. So we are trying to get here. So think about the route that we're going to need to take to get there. We're going to have to go from volume to moles, moles to moles, and moles to grams. Let's start with PIV-NERT. We need to solve for moles of our substance oxygen, and we're given volume. We're also given temperature and pressure, so it's like a traditional PIV-NERT equation. We're going to solve for moles, which equals PV over RT, plugging in my values, 1 atmosphere for my pressure, 5 liters, and notice what I'm doing here, I'm actually including oxygen. You'll see why in a second. Liters of oxygen, On the bottom here, we have our gas constant for pressure, which is 0.0821 liter atmosphere over Kelvin mole. And our temperature is 273 Kelvin. If you're thinking right now, if you're feeling a little lost, like why are we doing this? Hopefully after this first problem, it'll become a little bit more clear. But you know what? You might just be a little turned around right now, and that's okay. So I'm trying to solve for moles. Atmospheres cancel, liters cancel, the temperature cancels, and we're left with moles. So I got to calculate this out quick. And we get 0.223 moles. And list, whenever you have moles or amount, list what the moles is of. This is where you can get turned around. Remember, it's 5 liters of oxygen. Therefore, we have just solved for moles of oxygen. That's such an important step. If you forget to list your moles in the problem, or what the moles is of, you might think right now that you have moles of water and it's an easy step to convert to grams of water. That's not the case, though. We need to do a mole ratio. So we have 0.223 moles of O2. This next step is going to look very familiar to you guys because you've done this before. We just converted, let me clean this up a little bit. We just converted from volume to moles of Z. Now we have to convert from moles of oxygen to moles of the other thing, water. So I'm going to do my mole ratio. Moles of O2 to moles of water. And that mole ratio, I'm pulling it from up here. Oxygen, water. So we have 1 to 2. Lastly, moles is nice, but we now need to convert to our grams of Y. And so we're going to convert from moles of water to grams of water. And the molar mass, you're just going to take my word for it. If you add it all up, 18.02, or close to it anyway. And now we can calculate this out. And rounding to, let's see, we have got 3 sig figs in the problem, so this equals with 3 sig figs 0.0. One second, I must have made a mistake. Oh, sure enough, I got 8.04, and that's grams of water. If you need to, pause the video, take a look at the problem we did. I think you're going to realize that after the first step, when we were down, after we got to this step, this is all stoichiometry. And this was all ideal gas law from 12.2. That's it. If you can put those two together, you've figured out gas stoichiometry. I could write gas stoichiometry out this way. Gas stoich equals stoich plus ideal gas law. That's all there's to it. If you can put the two together, then you're going to be doing well in these. Okay. Now let's look at the next problem, because they're not all going to look the same. We do need to try at least 3 examples here. Tungsten is made industrially by reacting solid tungsten 4 oxide and hydrogen gas. The products are solid tungsten and liquid water. I'm going to stop right there. We are not given a balanced equation, so we have to make it ourselves. You cannot do stoichiometry without a balanced chemical equation. So it says that tungsten 4 oxide. Let's get some letters in here. Tungsten 4 oxygen is -2 charge. So if we that is not 4. That is a 6. Hopefully some of you noticed that. 4 there. That should be 6 there. Tungsten 6, oxygen 2. We do a little swap, drop, and reduce. 2 and 6 reduces down to 1 and 3. And you know I'm not including the 1 on the W. We don't need to on the tungsten there. Tungsten reacts with hydrogen, Brinkelhoff, diatomic, and the products are tungsten, solid tungsten, and water. I am leaving states out currently because, well, I think I'm running out of the room. Let's see, maybe I can fit them in. Gas, solid, liquid, and move this over a little bit. Solid. Okay. All right. Is it balanced? No, unfortunately it's not. We have 3 oxygens on the left-hand side, 1 on the right. Let's see if we can fix that. That would require putting a 3 there, which means we have to put a 3 here. And now I think we're balanced. Okay. What are we given? What are we asked for? We're given temperature, pressure. That's a good start. And grams of WO3. What can we convert grams to? Well, moles. We have moles of WO3, or we can find it. So we're given grams of WO3. Back to this little diagram here. Okay, so we're starting with grams of WO3. We know in our first step we're at least going to convert 2 moles. And what are we trying to get to? How many liters of hydrogen? That's volume. We're trying to solve for the volume of hydrogen. So we're going to have to convert to, if we're going to get to volume of Y, we're going to have to convert to moles and then to volume using Pivnert. That means we're going to start with the stoic first on this one. We're going to convert from grams to moles. Here we go. 875 grams of WO3. Of course, I don't have a periodic table by my side right now. Such a mistake, because I'm going to need to determine the molar mass of WO3. Without a periodic table, I am like, I'm lost in the woods without a knife or anything for that matter. WO3, what's that show? Naked and Afraid? I'm just without all tools to get me by. Except, I take it back. I think I've got a periodic table right here. Okay, we're back in business. W, that's the one that I have a hard time remembering. 183.9 plus 3 oxygens, so 3 times our 16. Okay, let's see. Back here, molar mass is 231.9. Okay. And now we have to get from WO3 to, well, we're trying to find volume of hydrogen gas, so we need to get to moles of that. Okay. So, little mole ratio, 1 to 3. We can solve this out, just stoichiometry so far. Okay. Okay, 11.3 moles of hydrogen. So, what's the deal? Why do we solve for moles of hydrogen when we need volume? Well, you know that we have an equation that we can use. The equation is Pivnert. And we can solve for volume within that if we have these things. We're going to need N, R, T, and P. Well, you always have R. Hope you know that you always have R. And we were given T and P within the problem. So we needed to find moles, which we just did. So let's just plug our values in now. Our moles is 11.3. And liters atmospheres over Kelvin mole times temperature, 35 degrees Celsius. Oh boy, is that going to be the temperature you plug in? I hope not. What's 35 plus 273? 308. right? And then our pressure, which was given to us, is 0.980 atmospheres. Do a little calculation here. 11.3. Okay. There we go. And I get a, well, let's check my units, because I showed them. Of course, you should show them. Moles cancel. Atmospheres cancel. Kelvin cancels. We're left with liters. I got a value of 200 and rounding to 2 sig figs, 290. Well, that's 3 sig figs. Pardon me. Let's see, 292 Kelvin. Whoa, Kelvin. Where did I get that? Liters. I even circled it. There we go. Not so bad, right? Besides the part where your chemistry teacher is referencing Naked and Afraid. I don't know why I do that. I don't even have a TV. I've never seen the show. I don't think it's bad. I'm just going to bank on that right now. Okay, so methane, CH4, goes through combustion when reacting with oxygen in air. We're not given a reaction, so let's just do it. CH4 plus oxygen in the air. We're going to produce some things. Hey, look, they even told us. If the reaction produces some volume of CO2, and, we're not given the other product, but I think we both know what it is, right? It's water. So we're going to cancel we're going to turn our 4 hydrogens, the 2 on the right side to 4, like that. We're given 4 oxygens on the right-hand side, on the product side, so put a 2 there, and then I think we just put a 1 there. Yeah, we're good. Okay, so if the reaction produces 213, there's a volume of CO2, a temperature of CO2, which, what is that, plus 273? 296 Kelvin, and a pressure of 0.890 atmospheres, what volume of oxygen must have been used at STP? New temperature, new pressure. Don't let this problem scare you. It's really not that bad. We're given volume, temperature, and pressure of CO2. And we're asked to find something about oxygen. Let's go back up to that little chart. Okay. Clean it up. Go away. We're given volume, and we're asked to find volume. It's not bad. It really isn't. We're going to convert from volume to moles using PivNert. We're going to use our mole ratio, and then we're going to use PivNert again and get back to our volume. That's our steps. Watch for it. We're going to do a 1, 2, 3. Okay. Can we solve for volume? Can we solve for moles? We've got equation, and moles equals PV over RT. We were given our volume, our temperature, our pressure. We should be good. Start with our pressure times our volume, 213, times our gas constant, times our temperature, 296 is what we said. That's going to give us moles. And I did the thing I told you not to do. If we have liters, let's include liters of what? That was our liters of CO2. There we go. Okay, so we're going to cancel some things out. Atmospheres cancels, liters cancel, Kelvin cancels. We're going to have an answer that's in moles. Divide that. And that gives us 7.80 moles. Specifically moles of CO2. Remember, we still have to convert to oxygen. So let's take that value, do a little copy and paste. There we go. And convert that using a mole ratio to the thing that we want, which is not carbon dioxide, it's oxygen. So go to moles of O2, and that ratio is 1 to 2. Okay, so we're going to have double the amount of moles from what we had before. That's 15.6 moles of O2. But we're looking for volume, and we can get volume using PV equals nRT. Volume equals nRT over P. Plug in your moles of oxygen. Plug in your gas constant of oxygen. That's sloppy. Kelvin mole. And let's see, where else? Temperature 296. Oh, what am I doing? Not 296. Yikes. Whoa. What volume of O2 must have been used at STP? We have a new condition, a new temperature, a new pressure. So let's plug that new temperature, then that new pressure in. Our new temperature is 273 Kelvin because it's STP. And at STP, we have 1 atmosphere. And if we calculate that out, I really ran out of room on this one, didn't I? Just copy and paste it when that happens. Okay. Equals, just checking my units now. Moles cancel, Kelvin cancels, atmospheres cancel. We're left with liters. That's great. And there we go with 3 sig figs. The answer is 350 with the decimal liters. Got it. Oh, not so bad. Thank you. If that was a lot of work, and I'm glad you made it to the end here. You deserve a pat in the back. 12.3 practice. We got 4 problems here. I will be uploading the key, as I always do, to Google Classroom. Look out for that. Later this week, we're going to have a quiz. Check updates on Google Classroom. Have a great day.